In this video, we're going to introduce the concept of Taylor Maclaurin series. The goal here is to represent a function with a power series. So let's assume that a function f of x can be represented by a power series of the form summation n equals 0 to infinity c sub n times x minus a to the power of n. Let's expand out this summation. We get f of x is equal to c sub 0. We obtain this term by plugging n equals 0 here. And c sub 1 times x minus a, that's the term n equals 1. And c sub 2 times x minus a squared, that's the term n equals 2. And c sub 3 times x minus a to the power of 3, and we obtain that term by plugging in n equals 3. The interval of convergence is x between a plus r and a minus r, and the radius of convergence is capital R. Let's derive the coefficients c0, c1, c2, c sub 3, and so on in terms of the function and the derivatives of the function. So let's plug x equals a into the function, into f of x, and we're going to get f of a is equal to c sub 0 plus c sub 1 times a minus a, which is of course 0, plus c sub 2 times a minus a squared, and so on. All these terms are 0. So the only thing that remains is c0. So we have now obtained the first coefficient c sub 0 as f of a. This is equal to f of a. Let's obtain the other coefficients by taking the derivatives of f of x and plugging in x equals a. So now let's take the first derivative, f prime of x. Derivative of c0 is going to be 0. Derivative of constant is 0. Derivative of this term, c sub 1 times x minus a, will be c sub 1 times 1. Plus, derivative of this term is going to be 2 times c sub 2 times x minus a. And derivative of the third term is going to be 3 times c sub 3 times x minus a squared. And derivative of the fourth term would be 4c4 times x minus a cubed, and so on. Now let's plug in x equals a into the first derivative. So we get f prime of a is equal to c1, and all these terms will be 0 because they're all powers of x minus a. So that's going to be plus 0, and so on. That means we have c sub 1 is equal to f prime of a. All right, so now let's look at the second derivative, f double prime of x. The second derivative will be 2 times c sub 2 plus 3 times 2 c sub 3 times x minus a plus 4 times 3 times c sub 4 times x minus a squared. Notice we don't simplify 4 times 3 as 12 because we want to develop the pattern. That's the reason. Similarly, 3 times 2, we don't simplify that. We just write it as 3 times 2. So let's plug x equals a into the second derivative. We get f double prime of a is equal to 2 times c sub 2 plus, and all these terms will be 0 because they're all powers of x minus a, plus 0. 0 and so on. So substitute, now solve for c sub 2, we get f double prime of a divided by 2. So now we have developed the second coefficient in terms of the derivative of the function. Let's take the next derivative. And by taking the next derivative, we should be able to see the pattern. So we're going to get derivative of 2 times c sub 2, that's 0, plus derivative of 3 times 2 times c3 times x minus a will just be 3 times 2 times c sub 3 plus derivative of this term is going to be 4 times 3 times 2 times x minus a to the power of 1 times c sub 4, and so on. So plug in x equals a into the third derivative. We're going to get f triple prime of a is going to be 3 times 2 times c sub 3 plus, and all the remaining terms have powers of x minus, or are powers of x minus a. That's going to be 0, so all the other terms are 0. Solve for c sub 3, we're going to get f triple prime of a divided by 3 times 2 times 1. So we can see the pattern developing, the factorial notation. So f triple prime of a can be written as c sub 3 times 3 factorial. In general, the nth derivative of f of x at x equals a can be written as c sub n times n factorial. Now let's solve for the coefficient c sub n, and we're going to get the nth derivative of f of x at x equals a divided by n factorial. Now we have developed the formula, the Taylor series formula. F of x is equal to summation n equals 0 to infinity c sub n times x minus a to the power of n. And we now know what these coefficients are in terms of the derivative of the function evaluated at a. This is equal to summation n equals 0 to infinity fn of a, the nth derivative of the function evaluated at x equals a, divided by n factorial times x minus a to the power of n. Let's expand out this, and if we expand it out, we get f of x is equal to f of a plus f prime of a times x minus a divided by 1 factorial plus f double prime of a times x minus a to the power of 2 divided by 2 factorial plus f triple prime of a times x minus a to the power of 3 divided by 3 factorial. And the interval of convergence is x is between a plus r and larger than a minus r. The radius of convergence is, of course, r. This is the radius of convergence. So we now have the Taylor series expansion of the function about the center x equals a. If the center a is equal to 0, then the Taylor series becomes a Maclaurin series. So basically just plug in a equals 0, we get f of x is equal to f of 0 plus f prime of 0 times x plus f double prime of 0 times x squared divided by 2 factorial plus f triple prime of 0 times x cubed divided by 3 factorial, and the radius of convergence is capital R. The interval of convergence is x is less than r, larger than minus r. So then we have a compact formula for the Maclaurin series. F of x is equal to summation n equals 0 to infinity, the nth derivative of the function evaluated at 0 times x to the power of n divided by n factorial. Now the intuitive idea is what's important here. We are reconstructing the function f of x as an infinite polynomial by evaluating its derivatives at x equals a. X equals a is, of course, the center of the Taylor series. All right, let's look at the question. Here we have find the Maclaurin series of f of x is equal to e to the power of 2x, and also find the radius of convergence. We start by writing down the general Maclaurin series formula, which is f of x is equal to f of 0 plus f prime of 0 times x divided by 1 factorial plus f double prime of 0 times x squared divided by 2 factorial plus f triple prime of 0 times x cubed divided by 3 factorial, and so on. Now I just need to add this thing here. 0 factorial is just 1, that's convention, and 1 factorial is also 1. So you can think of it as having f of 0 divided by 0 factorial, which is just 1. All right, so the key concept is to find derivatives of the function and to develop the pattern. So let's start with f of x. F of x is equal to e to the 2x. Let's differentiate, and we get f prime of x. Apply the chain rule, we get 2 times e to the 2x. And let's differentiate again and get f double prime of x. So we get another 2 coming out of the exponent because of the chain rule, and we get 2 squared. But we don't write it as 4. We write it as 2 squared because we're trying to develop the pattern. And now let's look at the third derivative, f triple prime of x. That's going to be 2 to the power of 3 e to the power of 2x. In general, the nth derivative evaluated at x is equal to 2 to the power of n times e to the 2x. This is the general pattern that we have developed. And we did that by differentiating a couple of times and seeing the pattern developing. General pattern. Now let's plug in 0 for x to find the derivatives evaluated at 0 so we can develop the Maclaurin series. F of 0 is equal to 2 to the 0, e to the 0 is equal to 1. F prime of 0 is going to be 2 to the power of 0, e to the 0, that's equal to, f prime of 0, that's going to be 2 to the power of 2 times e to the 0. That's going to be 2 times 1 is equal to 2. F double prime of 0, plug in x equals 0 into this expression for f double prime, we get 2 squared e to the 0, and we get 2 squared. In general, the nth derivative evaluated at x equals 0 is equal to 2 to the power of n. So the formula for the Maclaurin series formula is f of x is equal to f of 0, which is 1, plus f prime of 0, which is 2, times x, plus f double prime of 0, which is 2 squared, times x squared, divided by 2 factorial. And we can also put divide by 1 factorial, divide by 0 factorial, so we're consistent with the formula for Maclaurin series, plus the next one would be 2 cubed, x cubed, divided by 3 factorial, and the general term will be 2 to the power of n, x to the power of n, divided by n factorial, and so on. So we can write this in compact notation. We can write the Maclaurin series of f of x equals e to the 2x, f of x equals e to the 2x. We're writing the Mach series, and this is going to be summation n equals 0 to infinity, the nth derivative evaluated at 0 times x to the power of n divided by n factorial. And we found a pattern, and it's going to be summation n equals 0 to infinity, 2 to the power of n, x to the power of n divided by n factorial. This is the Maclaurin series of f of x is equal to e to the 2x about the center a equals 0. Now let's apply the ratio test to find the radius of convergence. So we have limit n approaches infinity, a sub n plus 1 divided by a sub n. This is equal to limit as n approaches infinity. Let's look at the n plus 1th term. So we get 2 to the power of n plus 1, x to the power of n plus 1, divided by n plus 1 factorial, divided by 2 to the power of n, the nth term, x to the power of n, divided by n factorial. Now let's simplify this. We get limit n approaches infinity, 2 to the power of n plus 1, divided by 2 to the power of n factorial, divided by n plus 1 factorial, and absolute value of x to the power of n plus 1, divided by x to the power of n. If we simplify this, we get limit n approaches infinity. We have the same base. The base is 2. Subtract off the exponents, so we get 2. And we have n factorial in the numerator. In the denominator, we have n plus 1 times n factorial. We can rewrite n plus 1 factorial in this way so that the n factorial cancels with the n factorial in the numerator. Times, and here we can simplify this. We have the same base. Subtract off the exponents, we get absolute value of x. So when we simplify this, we get limit as n approaches infinity, limit n approaches infinity, 2 times absolute value of x divided by n plus 1. Now, x is a fixed number. So when we divide 2 times absolute value of x divided by n plus 1, and n is approaching infinity, this ratio approaches 0, which is, of course, less than 1. That means the radius of convergence is infinity. So r is equal to infinity. And this series converges for all x between minus infinity to infinity. So the interval of convergence is from minus infinity to infinity. So let's review. The function f of x is equal to e to the power of 2x can be represented by the series summation n equals 0 to infinity, 2 to the power of n, x to the power of n, divided by n factorial for all values of x from minus infinity to infinity. The radius of convergence is infinity. The interval of convergence is from minus infinity to infinity. So what are the key steps in finding the Maclaurin series of a function? The first step is to find the function. Well, usually you're given the function, is to find its derivatives, f of x, f prime of x, f double prime, f triple prime, f fourth, and so on. Plug in x equals a. So then evaluate, find f of a, f prime of a, f double prime of a, f triple prime of a, look for a pattern. So we try to develop a pattern for the nth derivative of the function evaluated at x equals a. Then we just plug it into the Taylor series formula, summation n equals 0 to infinity, the nth derivative of the function evaluated at x equals a times x minus a to the power of n divided by n factorial. And if we have a Maclaurin series, then a is equal to 0. So if you have a Maclaurin series, you're just going to get f of x is equal to f of 0. And all we do is we basically plug a equals 0 wherever we see an a. And then the Taylor series becomes a Maclaurin series. So we get f of 0 plus f prime of 0 times x plus f double prime of 0 times x squared divided by 2 factorial plus f triple prime of 0 times x cubed divided by 3 factorial, and so on. And so that's the basic idea of finding the Taylor series of a function. All right, thanks.